Hey folks, this is Nathan Jones. Welcome to Beyond Arduino. I'm beyond excited that you would pick this workshop. I'm very excited to bring it to you. Hopefully you learn lots and have a great time. The whole purpose of the workshop is to kind of move away from the Arduino IDE and to do for ourselves the things that the Arduino kind of ecosystem had previously been doing for us kind of behind the scenes. And so I feel like this video is kind of important to kind of preface that so we have, so that we can talk about what it is the Arduino ecosystem is doing for us. And that sort of sets the stage for, what pieces we need to fill in come to the workshop. So I'm going to start by showing you kind of everyone's basic, I think, understanding of electronics when we start playing around with the Arduino, right? We have our computer here, which is running the Arduino IDE, and we have this conceptualization, or we're taught that when we call this digital write function with pin 13, we set it to high, that when we load our code through a USB cable onto our Arduino board, that somewhere on that board is a pin called D13, and when this line of code executes, that pin goes to, at 5 volts, right? A logical high signal, and that might be used to turn a light on and off or control a motor. We don't necessarily care how that happens. We just sort of know that somehow there's this connection between this line of code and something happening in the circuit. So what I want to do is kind of peel back the layers a little bit on what's happening as we're writing this code to get to the point where this pin goes high or low. To start with, let's take a look at the development board for the Arduino. So if we sort of take a look at what's happening on this development board, what we realize is that on this board is, number one, the microcontroller, the thing that we're programming. And in case of the Arduino Uno, this is the ATmega 328 microcontroller. And that's really the heart of the star of the show, right? Really, you could separate everything else on the circuit board into, kind of 2, maybe 3 big components, right? One is I've got a part of this development board, which is converting USB signals into something that can program my microcontroller. So in the case of the Arduino Uno, that's a USB to UART converter. I've got some little circuit that is helping power my microcontroller. And then maybe the third category is a lot of times these development boards have little buttons or sensors or LEDs that kind of help demonstrate what the microcontroller is capable of doing. So in the case of, the Arduino Uno, there's at least the little built-in LED, D13, right? And I want to show you that is in fact what's going on. We can confirm that by going to the product page for the Arduino Uno. If I scroll down here kind of towards the bottom on a lot of these product pages, there'll be a documentation section, and here I can find the schematics for the Arduino Uno board in a PDF format. And so this is what's going on my Arduino Uno. All right, it looks like a lot, but I'll orient you really quick to those 3 sections I just mentioned. Number one, down here is my ATmega 328P. So that's my microcontroller that I'm programming. That's the Arduino. And you can see on the right-hand side here, it's connected to those pin headers that we've all plugged stuff into. And there's some other stuff going on here to kind of help set that up. But, this whole section of the circuit is pretty much my Arduino. Over here on the left, I've got another microcontroller connected to my USB port. And so again, there's a bit going on, but basically this whole kind of lower left section of the schematic is just the part of the development board which is converting USB signals into UART signals, which are then connected to my Arduino that allow it to be programmed. And we'll talk about how that works kind of in a second. And then in the top portion of this diagram, this is just all the circuitry related to powering the Arduino. And there's a lot here just because on the Arduino Uno boards, there's a couple of different ways that you can provide power to the microcontroller. It can provide power through the USB cable. I can connect, a little DC jack into the board. I can have a wire going into the in. And in all these cases, we want to make sure that if multiple power sources are connected, none of them try to power each other the wrong way and blow up batteries and stuff. So, there's some protections in here to help regulate and make sure we get the right voltages, and we can plug in multiple power sources at the same time. But ultimately, this is all just sort of, assigning power to my microcontroller. So we can see on the schematic that those kind of the 3 big portions on this development board. So, when we are programming this thing, we're programming it through the USB to UART, and then this microcontroller is connected to these pin headers and it's doing something useful for us. All right. So then let's take a look at this microcontroller, the ATmega 328. If we kind of at the risk of oversimplifying something, right? We could say that all microcontrollers and really all computers, are built from processors, some CPUs that do very basic things like add and subtract numbers together, which are connected to a memory system that stores the instructions we want this processor to do and some of our data, and then typically some amount of peripherals that allow the processor to sort of talk to the outside world. And the CPU essentially pulls instructions out of memory. It will execute those instructions, and often that involves modifying data in memory. The peripherals are kind of necessary to let the processor talk to the outside world, and in most cases, these peripherals are what are called memory maps, meaning the CPU can read and write from these devices. The CPU can control these devices in other words, in the same process that it reads and writes stuff from memory. So the GPIO, general purpose input output, these are the sort of digital pins that we've used to turn LEDs on and stuff, is assigned a memory address. And the CPU, when it reads or writes from this memory address, the microcontroller is set up so that the result of that read and write amounts to controlling these pins. So let me also kind of try to prove that to you. If I search for the ATmega 328, this is a chip that's made by Microchip. So I can go to the product page for this microcontroller. I can download my data sheet. And the first thing I'll show you when this data sheet for my Microchip pulls up is that I can go to my overview and I can see a block diagram of the Arduino, or the Arduino Uno, right? The ATmega 328. And kind of like I was showing you before, right? The CPU is really the heart of the show here. You can see that it's connected to flash and RAM. These are the two memory banks, right, that store our instructions and our data. And it's also connected via this really big set of wires called the data bus to a bunch of other blocks. It's connected to my timers. It's connected to some analog comparators. It's connected to my UART and my SPI peripherals. It's also connected to the ports, port D, B, and C, that connect my microcontroller to the outside world. And furthermore, let's see if I go to, I think I want to show you next the GPIO. All right. So this portion of the datasheet describes exactly which registers, which parts of memory sort of map themselves to the GPIO. And what you'll notice, I want to bring your attention to this one right here. This is the register for something called port B. And it's the data register. So I can write to this register ones and zeros, and this register maps to the actual pins on my microcontroller, right? So port B, I've got port B 0 to 7. If I go now to the pin diagram for my ATmega 328, you'll notice along the outside here, all 28 pins, I have those port numbers. So you can see port B1, port B2, port B3, port B5. These are the actual connections, right? Just inside this pin basically is that port B data register that controls the value on this pin here, and whether that's high or low. Why does that matter? Well, let me share with you the pinout for the Arduino Uno. And what you'll notice here, let me get there, I'll go to the website, is that my built-in LED is connected to port B5. So if I can get my Arduino Uno, my CPU, to write to port B5, then that's going to change the voltage level on this pin. And if that pin is connected to my LED, built-in LED, then I can change the pattern on my LED by reading and writing from this memory. So let me demonstrate that real quick, because I feel like this is kind of cool. So this is my normal Blinky program, and let's see if I got it held up here. Okay, so you can see my LED blinking in this on-off pattern, and this is kind of starter code, right? I've got my digital write function that is telling pin 13 to go high and telling pin 13 to go low. Well, where did it go? My manual here tells me that port B is at memory address 25, and pin B5 is at pin position 5. So let me go to my, let me modify this, this piece of code right here. I'm going to tell, the Arduino Uno IDE, sorry, the Arduino IDE, that what it's going to do, instead of calling digital write, what we're going to do is we're going to tell it, hey, take 25, treat it like a pointer to an 8-bit integer, and give the value that's at that memory address a 1 left shifted by a 5. So we're going to put a 1 in, if it starts out here, 1, 2, 3, 4, 5 in this bit position, right? So I'm going to turn on port B5, pin 5, with this instruction. I'm going to do the same thing. I'm going to do something very similar down here, but instead of, oh, sorry, I forgot my OR. I'm going to OR this, OR equals this. So I'll take whatever value is in the port B data register, and I'll leave it unchanged except for this bit. Anything ORed with 1 becomes 1. All the rest stay unchanged. Down here, I want to now clear that bit. So what I'll do is AND this with the inverse. So what this expression here will do is put 1s in the whole register except for a 0 right at pin 5, and anything ANDed with a 1 is unchanged, but anything ANDed with a 0 will go to 0. So what I'll demonstrate this is that this can also blink my LED, and to prove it, I'm gonna reduce these delays here a little bit, right? So you can see my LED here that's blinking. See if I can get it in the camera, right? It's on, blinking on and off at a second, and if this works, then I'll see it blink much faster after I finish programming it. All right, so we're compiling. Forgive me for not having a fast forward button here. Well, hopefully I got my port selected. Oh, no, I don't. Oh, no, I got the wrong board too. Check me out. Okay, let's try again. Round 2. Oh. And there you go. My LED is blinking at a much faster frequency, which means this correctly compiled and it loaded, this code did. And so hopefully that proves that digital write, there's nothing fancy about the Arduino sort of IDE or what's going on in this microcontroller. What it amounts to is this processor being given simple instructions, which include reading and writing from memory locations that are also sort of mapped to these peripherals. And I can get my microcontroller to do useful things by writing code that reads and writes from these peripherals in useful ways. So now I've got the question sort of, okay, if I've got a program like this little Blinky program that I want to execute, how do I get that code into memory in the first place? Well, I got two options. One is I can put a program into my memory called the bootloader, which will always start running whenever power is applied to my processor. And what this bootloader will do for a couple of fractions of a second is listen on a specific communications port or a specific pin. In the case of the Arduino, it's listening on the UART port. And if it happens to see a very unique bit pattern on this communications port, a bit pattern that the Arduino IDE is programmed to send out as it's trying to program the Arduino device, then the bootloader will recognize that signal. It'll understand that what's following are data to be written, or is data to be written to the memory, which constitutes a program. And so it'll read data over this communications port and put it in memory and start executing it. That's kind of how the Arduino Uno works, right? We have this USB to UART converter, and that's connected to the UART peripheral on the ATmega328. So when the Arduino Uno goes to program this device, it basically just sends out this special bit pattern to the ATmega328. When the ATmega328 comes out of reset, it sees that bit pattern, it loads a piece of code into memory and starts running it. So that's option number one. Option number two is to use another peripheral called the debug peripheral. And this is a special peripheral which is is connected to the processor and memory in such a way that it can take full control over these parts of the processor, and it's also connected to the GPIO pins. You can actually see that in the Arduino Uno. If I go back to my overview, this top box right here is debug wire. Debug wire is the protocol that defines how this debug thing works for the ATmega, and this is super useful for two reasons. Number one, if my memory is blank to begin with, then I've got a bit of a chicken and egg problem, right? If I'm trying to use a bootloader to load a program into memory, but there's no bootloader in the memory to begin with, then I got to figure out some other way to get code into this processor. And so if my memory is blank, I basically have to use this debug peripheral. But the second way this is super useful, which is one of the biggest reasons I feel like to move away from the Arduino IDE, is that this debug peripheral can also turn stuff on and off for us while the program's running. So we can read and write from memory. We can actually halt the processor and single step through instructions, and this is super useful to figure out why broken code's not working. This debug peripheral is itself connected to pins on the microcontroller. And it's very bare bones. So typically what that means is in order to use this peripheral, we need a separate piece of hardware, what I call a debug adapter. And this debug adapter takes USB signals or sometimes Ethernet signals and converts them into the protocol that this device, the debug protocol that's this processor talks. So the SWD is a very common one. JTAG is debug wire was the one that we saw for the ATmega 328. And a lot of times this debug adapter, that's actually on the development board. So the one that the microprocessor we're going to be playing around with in our workshop, it's got the actual chip on there that we're going to program to do useful stuff, and then also on the board is a debug adapter. Additionally, a lot of these debug adapters these days come with a connection to the microcontroller's UART port. So what that does is that allows us to connect our debug adapter to our computer via USB cable and access two things at the same time, the debug peripheral on the microcontroller and a UART port. So we can use that to sort of send data to and from a serial device on our computer. Okay, so at this point, we have this understanding that to this development board, it's got a microcontroller on it, which is taking a very simple program that essentially reads and writes from memory to do useful things. So the last question we kind of want to ask is, okay, how do we compose this program here of very simple instructions, right? How do we go from my Arduino code to the actual thing that runs on the microcontroller? That process happens in a couple of steps. So if I consider main.ino sort of like my main file in my Arduino project, this is effectively a C++ file. So the first step is to use a program called the compiler that will convert my C++ code or my C code into what's called an object file. You can see kind of here that the typical file extension for that is .o. Main.o is the object file that corresponds to my main.ino source code file. And this file itself is not ready to run because while it has the instructions that are the representation of what I've written in my code, it does not have any definition for the functions that I've called like digital write. I didn't put digital write in my code, it's somewhere else. So the compiler, doesn't have that information when it makes main.o. And additionally, it doesn't have information about where this thing's going to go in memory. So, a lot of the sort of retrieval of specific values out of memory or jumps to specific spots in memory in order to execute loops and go to other functions is not programmed just yet. The compiler also needs to get the source code for what I'm going to call the Arduino HAL. HAL stands for Hardware Abstraction Language. This is more C code that actually provides an implementation for functions like digital write. And so if I go to, so I'm going to go to my GitHub here, and because I've started a little repository. You can go to GitHub. You can find the source code for the Arduino. If I go in here into this folder, I'm going to open up wiring_digital. This is actually a C file. If I scroll down a little bit, you'll notice that here on line 138, I've got a definition for my function digital write. And, it's doing some stuff for me, right, to make sure that there are, what I've given it is a correct pin and that the pin doesn't have a pulse width modulated signal on it. But ultimately what this comes down to when I write a value to a pin is I'm either clearing a bit if it's low by anding the value in this register with, the 0 in the bit position I want, or I'm setting it high by ORing it with this bit position, which is exactly the same code that we wrote here to turn that LED on and off manually. Okay, so all these Arduino functions that you know and love, they are all C or C++ files that get compiled into a whole variety of object files. The last thing that we kind of need before we start putting stuff together is startup code. And this is typically written in assembly. So there's an assembler that converts the assembly file into an object file. The startup code, it does a handful of stuff. It basically sets the microprocessor or the microcontroller. It sets it up prior to your main, your setup function running. And so that can involve sort of clearing out memory and copying stuff to the correct location. If you're using C++, then the startup code might call all of your, constructors. And so then we need that in sort of an object file to continue. Once I have all the object files for, my program plus any hardware abstraction language functions I'm going to use in my startup code, then I can combine all those things together with a program called the linker into my final executable. And the linker also will sort of read something called the linker script to tell it or help give it some instructions as to where these code files need to go in memory. And the linker will be the thing that sort of finally resolves all these references. In my main.o, when I call this digital write function, the linker will put that digital write function somewhere in memory, and at my line of code in my setup or my loop function where I call digital write, the linker will put in that spot the actual jump instruction to the correct spot in memory or what have you. And then the output of the linker is this binary or executable file, which is essentially just a giant list of the instructions and the data pieces that will go into memory, so that when my Arduino starts up and starts executing code, it'll do the thing I asked it to do. So where does this kind of leave us, right? Well, the reason that I wanted us to kind of go through this is to give us that roadmap of what pieces we need to find in order to do this process with a new microcontroller. So, number one is I'm going to have my hands on a development board typically to start, right? We're going to have one in the workshop. But it'll be important to know, number one, how the manufacturer is instructing me to program this board, right? Is there a bootloader in there somewhere that I can use? And so I can just sort of load a program over UART or over USB? Or does it need a debug adapter? Does it have a debug adapter on the board? Once I can kind of answer a few of those questions, or at the same time, I'm going to ask myself, secondly, okay, what sort of IDEs were recommended by the vendor? The IDE typically has basically all of this stuff, right? The compiler, the assembler, the linker, the startup code, the linker script. So as long as I can find a supported IDE, I typically don't need to worry too much about this process. And then lastly, where do I get these functions that let me do really useful, easy things like digital write 13 and not have to worry about finding the correct port in the reference manual and stuff? Essentially, where do I find my hardware abstraction language? And once we got those three pieces, right, I've got my development board, I know how to program it, I've got my IDE, and I've got my hardware abstraction language, then I can do this with my new microcontroller. So anyway, I hope that was useful. I'm very excited to see you all at the conference. That's all I got.